Derivatives. When we first learned this concept, it is most likely synonymous with slopes. More precisely, if we have a function f of x, we can plot the graph in our usual coordinate plane. The derivative of f at a is then the slope of the tangent at the associated point. This is a good intuition of derivatives, or is it? It's completely fine for functions like this, but what if we have functions like this instead, where we have two inputs, x and y, and two outputs? Then we need 4 dimensions just to graph this function properly, let alone making sense of slopes in 4 dimensions. So if we want to generalize the notion of derivatives, derivatives cannot be slopes. On a similar note, usually integrals are thought of as areas. More precisely, if we again have a function f of x, then the integral can be thought of as the area under the curve. This is a good intuition of integrals, or is it? This is not as problematic as the derivative one, but this is still not the best intuition moving on. So how should we actually think about it? Let's rethink derivatives and integrals. Linear maps might not seem relevant, but it actually is the key here, so let's dive into it. We will first look at linear maps in 2 dimensions to get the hang of it. Linear maps are required to have these properties, which we are going to demonstrate using the animation we have just seen. In this illustration, we see that parallel lines stay parallel, and if the lines had even spacings, they will space evenly after the map. If you didn't catch it, note where the yellow and white lines are after the transformation. They are still parallel to each other, and although the spacings have changed, the lines are still evenly spaced. The final property is that the origin is fixed. The origin is the red dot in the middle here, and before the transformation, the origin was there as well, so the origin is fixed. The nice thing about these linear maps is that we can simply track where these 2 points go, because once we know that, we can already create a grid system out of these 2 image points. In other words, these 2 points carry all the information of the linear map by creating an alternative coordinate system. More concretely, if we have some random point, say 1.30.8 in the original coordinate system, then after the linear map, it is still 1.30.8, but in the new warped coordinate system. So once we know where these 2 points are, we know where every other point goes. To represent the locations of these 2 points, we need to refer back to the original coordinates. The point 10 on the horizontal axis gets mapped to the point 1.33 minus 0.73 in this case, and 01 on the vertical axis gets mapped to the point 1.17, 0.75 in this case. These 4 numbers completely determine the linear map, and so we usually represent them in an array like this. By convention, the first column represents where 10 goes, and the second column represents where 01 goes. This array of numbers is called a matrix, capturing the essence of a linear map. Another thing about linear maps is what it does to 2-dimensional regions. Even though the region will be distorted, areas of any region actually scale by the same factor. In this example, this area grows by a factor of about 1.86, so for any region, the area also grows by exactly the same factor. This scaling factor is the determinant of the linear map. If the linear map involves some sort of reflection, for example in this case, we are simply reflecting along the horizontal axis, then even though the area hasn't changed, the determinant is -1 rather than 1, where the negative sign means our orientation has changed. As I said a minute ago, a linear map is summed up in a matrix, so we should be able to compute the determinant just from these 4 numbers. In fact, we can. In this 2-dimensional case, we can compute by first multiplying the 2 numbers on the main diagonal, then minus the product on the 2 numbers on the other diagonal. However, this formula is not very crucial in understanding, so I'm not going too deep into it for now. Let's reduce to one dimension. As we said before, these three are the requirements of being a linear map. The first one isn't too relevant because we only have one line to deal with anyway. But the next two requirements mean that we are restricted to just scaling, so linear maps in one dimension are scaling. In 2D, the linear map is represented by a matrix like this, but in 1D, we only need to know where 1 goes, so the matrix reduces to just one number, which is the scaling factor. What about the determinant? Well, in 2D, the determinant is the scaling factor for areas, so in 1D, we replace areas by lengths, but the scaling factor for lengths is just the scaling factor in general, so the determinant is just that number inside the matrix in 1D. So we have what we need to know about 1D and 2D linear maps. What about derivatives? Let's think of one-dimensional functions this way, transformations of the number line. So this is how squaring looks like. We are talking about a general function, so the spacings can be uneven. Now pick a point on the input number line, say a. Obviously, under the function f, it gets mapped to f of a, so what we actually want to know is the behavior of f on the neighboring points. So let's zoom into the neighborhood of the point a and observe what f does to it. It does look like a scaling, and in fact, the neighboring points are about 3 times apart. It's not exact, but when we zoom in even further, the discrepancy from this scaling approximation would gradually vanish. Here is a little technical remark. In general, the point A will move to f of a rather than just staying put, so in fact, we have been centering our perspective on a. This means that we can treat this as a linear map, well, sort of, because it's just approximately one. In this case, the linear map is represented by the matrix 3, because this is a scaling by a factor of 3. This is the Jacobian matrix at the point A for this one-dimensional function f, and the number in the matrix is the derivative, denoted f prime of a. In other words, the derivative is the scaling factor near the point A. It's important to note that this depends on where a is. If we have moved a somewhere else instead, then the function near a looks like this, and there is even some sort of reflection involved. Points on the right of the red points go to the left of it, with a scale factor of 2, so we can approximate this with a linear map with matrix -2, and the derivative is -2. Even for the same function, the Jacobian and the derivative can be different depending on a. Similarly, for a two-dimensional function with 2 inputs and 2 outputs, we can visualize this using transformations of the coordinate plane. So this function looks like this. It doesn't look linear, and lines aren't even lines under the function f. But again, if we pick a point AB and then zoom in far enough, after centering our perspective on the point, it looks like a linear map. Again, this is not exact, but we can take the closest linear map approximation. This is the image of the exact linear map with respect to the original coordinate system. As discussed in the first chapter of this video, the matrix for this linear map should look like this. This is where 1, 0 on this coordinate system goes, which is 1, 1.5. On the other hand, 0, 1 went here, which is -1, 1.5. This matrix, just like in the 1D case, is the Jacobian matrix at the point we are studying. Again, the Jacobian matrix depends on the position AB of the point. Just to recap what we have done so far, the Jacobian matrix is the matrix representing the best linear map approximation of f near a particular point. But given the function f and the point AB, how do we compute the Jacobian matrix? To do that, we have to consider the components of f. For example, in this function, we can break it down into f1 and f2 components. We can then define another function g, which is basically f1, but the second input is fixed. Then the function g has 1 input and 1 output, something we know how to deal with. Visually, what g does is to take the x-coordinate of the points on this horizontal line, apply the original function f to the horizontal line, then take the x-coordinate again. Or equivalently, you can think of projecting back onto the horizontal line. Now what is g prime of a? We have said before that it should be the scaling factor of g near a. Equivalently, we want to see where this point 1 unit to the right of a goes. For example, if it ends up here after projecting back to this horizontal line, in this case, g prime of a will be 3. But how does it relate to the Jacobian? The first column is precisely asking where this point goes, and g prime of a simply extracts the x-coordinate for us. Usually, we don't say the function g explicitly and denote g prime of a directly in terms of f1, but this is nothing new, just a notation to save us the trouble of explicitly defining g every time. In practice, we still need to at least think of g to do the differentiation. This helps us find the first number in the Jacobian matrix, and the other numbers are quite similar. For example, if we want to find this entry, we simply define another function that extracts the y-coordinate instead. More precisely, we define another function h using the second component of f instead. And similarly, we can denote h prime of a using a similar notation, so now the second entry is equal to h prime of a. What about the second column? We now consider yet another function, but on the vertical line instead, because we want to see where this point on the vertical line goes. So this time we define two other functions that are fixed in the first input instead, and we have a very similar notation for their derivatives. The function p extracts the x-coordinate, while q extracts the y-coordinate, so the entries in the second column are p prime of b and q prime of b respectively. So writing in our other notation, this is the Jacobian matrix. But remember that these notations simply correspond to how we compute the entries, because in essence, it is still the matrix representing the best linear map approximation of f near the point AB. But there is another thing we can say about a linear map, which is the determinant, or the scaling factor for areas. Not surprisingly, this determinant is called the Jacobian determinant, a measure of how much areas scale near the point AB. Again, the determinant can be computed using the matrix by the method we have discussed previously. These two concepts are crucial when it comes to changing variables, as we will see in the second half of the video. Think about a heavy rod and we want to find its mass. Unfortunately, the densities at different places are different, and the density is described by the function f of x denoting the position on the rod. So how do we find the mass of this rod? Well, we can chop the rod into smaller pieces, then find the masses individually, then add them all up. The reason we want to do this is that the length of each little rod is so small that we can approximate it to have uniform density. Let's say the density at this point f of x star. So we assume f of x star to be the density throughout this little rod. Then the mass is the density multiplied by the length of the little rod. Repeat this for all the little rods, and summing the little masses up, we get the total mass. This is not perfect, but as the length of the little rod decreases and there are more and more of them, we get closer to the true mass. This process is denoted using an integral. Here, a and b represent the two endpoints of the big rod, and f of x dx can be thought of as the masses of the little rods. What about in 2D? What is the mass of this region if the density at each point is given by f of xy? Well, again, we divide this region into smaller pieces, this time using rectangles. However, we might see something that is not a rectangle. Feel free to ignore them, because as the rectangles become smaller in size, these will have negligible contribution to the mass anyway. For each of these rectangular regions, we again assume the density is uniform, say the density at this point x star y star. The mass of this little rectangle is then the density multiplied by the area of this little region. Again, repeat this for all the rectangular regions and add the little masses up. This is also represented by an integral, but this time d represents the region and f of xy dx dy is the mass of the little rectangular regions. But how do we actually find this mass or equivalently compute this integral? To do this, we add the little masses in a strip first, then add them all up. Let's focus on the middle strip here. We deliberately take the points all on the same vertical line so that we can imagine a one-dimensional vertical rod. The difference is that the strip is not one-dimensional, it has a width, so the mass of the strip can be approximated by the product of width and a one-dimensional integral. It's not really that scary. F of xy dy simply refers to the mass per unit width of the small rectangles. Or equivalently, if we combine the factor of width, this really refers to simply the mass of each rectangle. The other thing to note is the endpoints of the integral. They refer to lower and upper endpoints of the strip, but different strips have different endpoints, so the endpoints depend on x, the position of the strip. This entire integral depends on which strip we are talking about, or x, the position of the strip. So let's call this g of x, just some function of x. This is the mass per unit width of the strip. But this is exactly what we were doing with the one-dimensional rod, the only difference being that the density is described by g, not f. Essentially, each little rod contains the mass of an entire vertical strip, so we integrate g of x to find the mass accordingly. To summarize, to compute this integral, we consider each strip first, which is the mass per unit width of a strip. Then, we integrate along the horizontal axis. Not too surprisingly, we can also use horizontal strips first, which leads us to the similar formula here. These are again just ways of computing the integral. Conceptually, we are still just adding up masses of these little rectangles. Sometimes, the fact that the endpoints are not constants can be annoying, and so we might want to change variables. Let's think of a rod again. Just like in the previous setting, the density is described by f. This time, the endpoints are described by g of a and g of b respectively, where g is just another function. As we have discussed just now, the mass of this rod is simply the integral shown here. But seeing the endpoints being g of something isn't it tempting to consider another rod with endpoints a and b instead. We want a rod so that when we apply g to the bottom one, we get the original one. So if I have a random point u here, we want this to correspond to the point g of u on the original rod. The density at this point is given by f of the position, which is f of g of u, and so we want this density on the bottom rod to be described by f of g of u as well. That doesn't make the two rods have the same mass because their lengths can be different, but here's the trick. We always chop the rod into smaller pieces to find the mass, but let's focus on the one containing the point u. It's mapped to some little rod containing g of u. These two little rods have the same density f of g of u, but different lengths. How different are they? The scale factor induced by g near the point u is precisely g prime of u, so the length of the little rod scaled by this factor. So if we add this factor into our density, we can make the two little rods have the same mass. U was arbitrary, and we can do the same thing to the other little rods, and so the mass of the original rod should now be the same as our modified bottom rod, which is this integral on the right. This formula is usually known as integration by substitution, but how does that work in 2D? Quite similarly, we consider a region with density given by f of xy. However, the region is g of d, where d is just another region, and these are related by the function g. The mass of the region g of d is simply this integral on the left, and we want to find the right density on the region d to give the same mass. Again, if we have some random point uv in the region D, after mapping by G, it ends up in G of uv, and we have density f of G of uv at this point. This doesn't make the two regions have the same mass yet. A small rectangle in region D containing uv will map to some region containing G of uv. These two regions have the same density but different areas. The corresponding scale factor for areas near the point uv is precisely the Jacobian determinant at the point uv. So by adding this scale factor to the density, the two small regions now have the same mass. Here, I simply use this J thing to denote the Jacobian determinant, and so the mass can be represented by this integral. Except this is not quite the full story yet. What if the Jacobian determinant is negative? The determinant being negative simply means reflection is involved during the linear map, but the area itself doesn't care about a negative sign, which means the scale factor should be the absolute value of the Jacobian determinant, and so this should be the correct change of variables formula. Immediately you might have a question. What about the 1D changing variables formula? By the same logic, the scale factor should also be an absolute value, but it isn't. If the scale factor is negative, it would flip the rod and would really have a negative contribution to the integral. Because of the way we define a one-dimensional integral, if we flip the endpoints around, the sign changes, even though we are talking about the same interval. So inherently, the one-dimensional integral already considers the orientation of the rod. So if the scale factor is negative, it would really have a negative contribution. Contrast this with how we define a two-dimensional integral. Orientation is not built into its definition, and we always say the integral is defined on a region, never specifying its orientation. There is another detail that is often glossed over. G cannot look something like this. Because of the absolute value, this bit would be integrated twice. We don't want this to happen, and so we require that G doesn't do this. In more technical mathematical terms, we say that G is injective. Again, there isn't such restriction on G in the one-dimensional case, but I will leave the details out for now. Maybe you can flesh out the details in the comment below. Essentially, it hinges on the fact that orientations are built into one-dimensional integrals. So these two formulas can be used for changing variables with the additional requirement that G needs to be injective for the two-dimensional case. Suppose you have a unit disk and you want to integrate f over this region. However, as we discussed before, we need to compute in one of these two ways. Annoyingly, the endpoints are square roots, which can be frustrating to deal with. And to be honest, whenever you see a circle, it probably is a crime not to consider polar coordinates, because in the polar world, we have this much simpler region, where r ranges from 0 to 1 and theta ranges from 0 to 2 pi. Here, the function g goes from the polar world to the Cartesian world, and so g looks like this. So according to our change of variables formula, we want to compute this integral instead, but now the region T is rectangular, and the original region D is simply g of t. Now all we need to do is to figure out the Jacobian determinant. To do this, recall how to compute the Jacobian matrix first. Here, G1 and G2 are the first and second components of the outputs of G. Then all we need to compute is each of these entries and do the crisscrossing to get the determinant. It's a good exercise to do this yourself, but in this case, there is a much more direct way of finding the Jacobian determinant. Let's consider a very small rectangle with r theta as one of its vertices, with width delta r and height delta theta. After applying the function g, first off, the point r theta maps to the point r units away from the origin and at an angle theta from the horizontal. The bottom edge of the rectangle has theta stay fixed, and so it is mapped to a sort of extension of the line from the origin. the length of this extension is simply delta r. What about the left edge of the rectangle? It has r stay fixed, so it should map to a circular arc. The change in angle is delta theta, so the length of this circular arc is r delta theta. So this part of an annulus is where the small rectangle gets mapped to. When delta r and delta theta are small enough, this will look more and more like a rectangle, so the area is approximately r delta theta, while originally the area was delta r delta theta. This means that the scale factor for areas near the point r theta is simply r, and so this is the Jacobian determinant. This means that the change of variables formula from Cartesian to polar looks something like this, r being the Jacobian determinant. One very standard exercise is to compute this integral and see what cool things come out of it. Before you go, there are a few things I want to say. First, I have recently created a Patreon account. No obligation whatsoever. Consider supporting this channel if you want to and can afford to, because these videos do take a huge amount of time and effort to produce. Secondly, there is always a Google form linked in the description to gauge your math levels, and from the form, since most of you know the basics of derivatives and integrals, I made this video assuming that knowledge. And also why, third, I made this video series in the first place. The video series tackles a problem mentioned in the introduction of the video series. This video was made as the prerequisite for the final video of the series, so do consider watching the introduction video so that the final video makes sense. If you enjoyed this video, like, subscribe, hit the bell and leave a comment below so that more people can watch this. See you next time!